brake to bend the sheet metal, and you need a drill and a rivet gun. That's it. This thing, you need a foundry, right, to do this casting. You need a press to make all these parts. This is sheet metal too, right? Lot bigger infrastructure required behind this.
Orange too, it's painted.
Yeah, and it's painted. Yeah, you need well, yeah, that's non-trivial, right? You need compressed air. But what's cool about that stove in the back, the Darfur stove, is it's actually stamped. The rough cutout is stamped in India. And then they ship it flat packed because it's still just sheets. And then when they get to Darfur, all they need is a brake and a drill and a rivet gun, and they bend it up right there and assemble it. And they've done a few 100,000 of those. It's been pretty successful. The motivation behind that actually was that there was a huge incidence of rape in the camps, the displaced person camps, because women would go out and collect firewood. And their motivation was that if they could make a more efficient stove that burned less wood, they could lower the risk to women. And so they made this clean burn and cook stove, but they had to get it there and make it there somehow. So kind of if you Google the Darfur stove, you'll see more information about it. It's a pretty cool story. All right. The next one let's talk about is the Jaipur foot. So this one's gotten a lot of press. If you guys have read The Fortune at the Bottom of the Pyramid, you would have read about it. I'm going to pass around some Jaipur feet. Don't put these in your mouth. They're disgusting because they're used.
Okay.
But we have a lot. Yeah, well, come on, children. We gotta. Okay. So lots of good stuff to think about with this. And I'll hold one up. Okay. So here's a Jaipur foot. This is the most widely distributed prosthetic foot in the world. There's 24,000 of these given away a year. They've been around since the 1960s. They're considered really a revolutionary developing world technology because they enable people to get out of the house and work and do all these good things. What do you think is really novel about the design of these? Ooh. Well, I'm going to come back to that. How do you think they're manufactured? Nope. Nope. I'm sorry? Yes. The insides are carved. Yeah, I'll show you in a second. But what about, just think about the features though. Like what socioeconomic factors were they thinking about? It looks like a foot, right? It's not some wood block or like peg leg you're clomping around with. It looks lifelike, and one of them has nail polish. You notice? Yeah. Yeah, no, but it actually has toenail features, and it's color matched to the skin. Right? That's really clever. What else do you think is important about this?
It's one piece.
It's one piece. Yeah, that's, yeah, a few parts. But it's also flexible. Right? Look at this. You can flex on it. Why do you think that might be important in a culture like India? You got a picture of it, right? Yeah, squatting. Yeah, hugely important because there's actually more cell phones than toilets in India. I don't know if you knew that. Yeah, but the majority of the population squats when they defecate. So being able to squat down is really important. So a conventional prosthetic foot that you buy in this country will attach with this metal coupling. It's called a pyramid, where you put a bunch of set screws in and you can align the foot and stuff. And it's a pretty beefy, expensive piece of metal. This doesn't have any of that. How do you think this connects to the socket above it? Yeah, it slides inside the socket. And how's it held? No, not firmly. Some of the feet you'll see have a shoulder right here where the socket can kind of butt up against it. But there's holes in some of the used feet. Oh, the one you're holding, you can see it. There's wood screws. And so, you know, we're redesigning this right now in my lab. And the wood screws are a really like low-cost solution, and you can do it out in the field. But it's a pretty crappy coupling. They loosen up quickly. You'll see some of the used feet have like a number of old holes in them where the foot has had to be remounted. Yeah. So to show you the inside of this, I'll bring you through the manufacturing process. They cost about 10 bucks. Yeah, okay. So, as somebody said, the foot starts with these carved foam blocks. So, here's a forefoot. Here's the ankle block made out of wood, so you can screw wood screws in it. And then here are the toe features. These are all actually rough cut. And then what they do is they wrap all these foam blocks with nylon corded rubber banding. And what this does is it gives the foot a lot of tensile strength, particularly in the sole. Because when you bend your foot, you have a lot of tension here. And the foot could rip in half otherwise. It also, they kind of follow the same paths as your tendons would. And then after that, they wrap it with this rubber. Here's some strips of it if you guys want to pass it around. This skin-colored rubber, put it into a mold and vulcanize it. And this is the flash left over after the mold process. So under heat and temperature, the rubber flows and fills in the mold. And then they trim this off, and you've got your foot. This one's made for an above-knee amputee where you screw a pylon into it, like a post. But that's how they're made. As you might guess, it's pretty labor-intensive. You know, one guy can do, I think, 2 feet in a day. And the bigger issue with the Jaipur foot right now, and why we're working with them, is they get a big variation in quality because they're handmade. Also, they have an issue with knockoffs because mom and pop shops will make fake feet, no joke, and sell them as if they're Jaipur feet, so it hurts the brand's reputation. So this is what they've been working on before we came in. Oh, by the way, I'll pass this around. This is called a Satch foot. This is a wooden block foot. This is your kind of normal low-cost foot, but it's got like very little flexibility, so you can't climb trees or, you know, squat or anything. Okay. Oh yeah, I think I passed. Oh, here you go. If you want to see the inside of the foot after it's made, yeah. Thanks, Michael. Yeah, you can pass that around. Okay, so when we came onto the project 2 years ago, this is where they were. This is a new Jaipur foot. Somebody said, you said injection molded, right, Jeff? Yeah. This is an injection molded polyurethane Jaipur foot. And they worked with the Indian Space Organization and Dow Chemical in India to try to formulate this foot to get the right flexibility and everything. And the way it's constructed is it has this rigid heel in the ankle, which you can screw into with wood screws. This is injection molded, and it has a threaded insert so you could put the pylon in. And then that is cast into the center of the foot, and around it is molded polyurethane. And these little expansion, these are for the polyurethane to expand in the mold, and you cut these off afterwards. So this foot is lighter, which is nice. It's mass produced. But can you think of why this foot might have issues? And I'll give you a hint. That foot, the regular Jaipur foot lasts an average of 3 years in the field. This lasts an average of 4 months. Why do you think? No, it's actually not repairable. And you'll see when these things fail, when you look at some of the used ones, you'll see that the heels wear down and it breaks the cords, or you can break them in the forefoot and they'll split there a lot of times. Well, why do you think the injection molded one fails?
Compromised with the material, so if you make it flexible, it might not be as durable.
Yeah, but flexibility and durability may not go together.
That's what I'm saying.
Yeah. Okay, maybe I'm not understanding.
So with this foot, you have different materials that are serving different purposes.
Yeah.
So you have like the flex based on the core design.
Yeah.
And then you have the durability on the outside.
Yep.
So here you have a single material, so you're compromising.
Yep, that's a good point. And to add a bit more detail about that, remember this one had those nylon bands, right, running in the high tensile stress area. This foot has none of that, right? It's just regular polyurethane, and when you stretch it, at some point it's going to rip. To add to that, what makes that even worse is think about the stress concentration right here, where you go from a rigid keel to a flexible foot. So what happens is the front of these feet just break right off. Yeah. Yeah, it is a problem. So this foot hasn't been commercialized yet. And what we're trying to do is, I'm going to tell you about this in a couple weeks. We'll do another case study on the feet we're doing, but make a very high performance foot that's close to what you can buy here, but still hitting the price point of this foot and making it cosmetically acceptable and everything. Cool. All right, so that wraps up the development technologies. And again, you know, look at this scale difference between these guys and these guys. It's mind-blowing, but I think in all these situations, they hit upon something that people really want, right? And people would buy it and accept it at large volumes. All right. The other part of this lecture I wanted to talk about was manufacturing / prototyping. And I guess the wheelchair is a good transition. Like, I may have mentioned this when I talked about the LFC in the last lecture, but I wanted to show you the seat pan of this, right? So here's a seat pan. How do we make this? This is actually plastic here, but the rest of this frame structure. Yeah, it's welded.
Fixtured and welded.
Yeah, exactly. It's fixtured and welded. But think about having to cut out all these tubes, having to fish mouth them, which means make them curved at the end so they can butt up against another curved tube. I think, yeah, if you look at these welds have been ground down a little bit so they're not sharp. So there's a huge amount of labor involved in making this. And when we designed this, we were really thinking about kind of village scale shops, you know, making hundreds of wheelchairs per year, not thousands. So when I brought the new chair in a couple weeks ago, that now has a single piece stamped sheet metal seat frame. So there's no tubing, there's no separate piece here, it's just all one piece, right? So that's a lot better for design for higher production. Yeah.
Quick question about this plot. One other thing that I could see in it was the right-hand side. It's kind of dedicated manufacturing of one product. A lot of the other companies are like already manufacture a lot of other stuff and probably can take on more risk. Does that play in as well? For example, Nokia, Honda, Toyota, except for the bicycle.
I think, yeah, maybe that's a good point. These companies were probably, I don't know about the history of the bicycle, but like these other guys were established making other things, so they could take on more risk. Shashi, I don't know, John was at the Tata seminar, but Shashi, who was here last week, made the comment that we're going to, like, the idea of the developing world product startup that makes one product is a tough proposition. Because it's hard to succeed with that one product. It's hard to make a profit. And I think even, you know, with our wheelchair, we've had to go into the US market. And that's probably going to be our big money maker. And so I think that's probably some of the challenges that these companies face, is that they're just trying to commercialize one product. I wanted to talk about prototyping a little bit. So I brought these in because this shows kind of the history of how we did the LFC. And this is really apropos to your projects because you're going to have to prototype things. And so they can be totally quick and dirty. So there's things in here, like I like this because this is when we were trying different coupling designs of how the levers go into the chain rings, right? So we welded up tons and tons of different architectures of how to do this, right? And bent them and screwed them up. This is another one. Here's another square one. This shows how we modified bicycle parts. This has a piece of water pipe inside that this axle, bike axle, is going into. But just showing quick and dirty prototypes. Yeah?
How much of this was really intended to be like, okay, we're going to make these 7 things, these are materials we need, we're going to build them, we did drawings first, and how much of it was like, this is what we have, let's see what happens?
But it was a mix, actually. Yeah, we just, like for the different, I have a bunch of different coupling designs in here. We just wanted to play around with different architectures for the coupling and see how it felt, right? See if it was stiff enough. And this coupling actually, I've cut off the lever, this is the brake bar. This coupling was plenty stiff enough in this direction, but side to side it was really floppy. And we only realized that after we made it. And then we thought about it, and it was like, oh yeah, duh, there's no moment of inertia going that way. That's why we still use a round tube, so it's stiff in both directions. But this is a good example of we did the calculations of the moment of inertia and the stiffness and the strength in this direction and made it, and then realized flaws in the design. So I think I am a real proponent of fail early and often and prototype like crazy. You'll learn a lot that you can't capture necessarily in analysis. Somebody asked about the anti-tip bars when I talked about the LFC. Here's the anti-tip bars. This is one. I brought two. I had these in my office, and I thought I'd bring them today. But they just bolt onto the back of the frame. This is the bottom part of the frame, but they bolt on here, and they prevent you from tipping. So we went through a bunch of prototypes of how to do this, and these are the quickest and dirtiest and simplest. Yeah, there's some parts in here, like this is a good example. So this was the bolt plate that our wheel bolted onto in our East African chair, this big, heavy thing. And when we initially designed this, when we made the first prototype, we water jetted it, right? Because we could. It was super quick to do here. Knowing that in Africa, we could use a hole saw, cut 2 holes, and then join them, and then just drill these out. So we can make it 2 different ways. We can make it in Africa, but we can make it faster here. Here's some hub flanges that are water jet. But you have a ton of prototyping capability here at MIT. And then I just thought I'd show a couple other quick and dirty prototypes. This was, I worked for Bluefin Robotics for many years, which is an underwater robot company. They make these kind of torpedo-looking robots that swim around autonomously. And we were talking about making a rope deployment system where out of the nose of the vehicle you could shoot some rope out, then fire a grappling hook at it, grab the rope, tow it back into the ship, so it would be easier to recover the vehicle than trying to pull the ship up to the side of the vehicle and maybe bump into it. So we were thinking about a bunch of different architectures of how to get the rope away from the vehicle, and one was a projectile kind of torpedo. And so this is just a really quick and dirty prototype that I made in probably a half hour. It's 4 pieces of aluminum that I cut on a shear and then bent in a brake. I riveted them. I put polyurethane foam, which you use to seal your windows, like around your house, so the thing floats. And then I guess I made it somewhat hydrodynamic with half of a Super Ball, but you can also do this, which is kind of cool. So this was a really nice, quick and dirty prototype that I actually brought down to the ocean. I brought this down by the New England Aquarium, and I was sitting there throwing it off the pier and seeing how it moved through the water. And there was a police officer kind of patrolling by me. Obviously a little nervous why I'm throwing around these bomb-shaped things. But I made sure to wear my MIT hat when I did that, so they knew I was from here. But it's an example of how you can really make something quick and dirty to prove a concept. Another one, nice fun story, is that Bluefin's robots are roughly shaped like a torpedo. They're kind of in this shape. And kind of in this shape. And my boss and I were having an argument about where to put a side thruster, because we wanted a vehicle that could move side to side and actually kind of counteract a side current as it's moving along so it could stay roughly straight. So ideally you'd want that side thruster at the center of drag going this way. Center of drag going this way is right at the center of the vehicle, but the center of drag flowing this way, it's not really obvious where that would be, right? And so my boss went through all this hydrodynamic theory to say oh, I think the center of pressure's up here, because of all these lift effects and stuff. And I was like, no way the center of pressure's way up there. It's going to be kind of near the geometric center of the vehicle. So what I did was take one of these underwater pool darts, right, which you can buy for $5 off Amazon, and then made this center of pressure measurement system, right? And this is just out of a coat hanger, and I drilled a bunch of holes in this thing, and I could pull it sideways through a tank of water and see if it spun at all. And when this was lined up with the center of drag, it would just stay perpendicular to the flow and move through. So again, really simple, quick and dirty prototype that, showed us not only like where to go forward in a design, but also helped validate some theory, right? So I think you guys should do this type of stuff in the class. And then the last example is a couple years ago, my girlfriend and I made these Christmas ornaments for our friends. They're laser cut, and they go together to make a Christmas tree, like this. And I keep these in my office because this was kind of a complicated design, right? So they go together like this, and you can hang them on your tree. It's a little Christmas tree. So this was kind of complicated, and before we cut out like 50 of these things with a laser cutter, we decided to think about, or decided to look at, like, would this actually work? So another thing you can do with prototypes is make like a functionally similar but much simpler quick and dirty version. So here's the same tree idea, which has a locking feature for the trunk, and the same locking features for the trunk and the tree part, just laser cut out of cardboard. And then when I was confident that would work, I made a version that looked the same but still out of cardboard. And then when I was confident that would work, we made the real ones. So you have a lot of prototyping resources here. I think me and Michael and your mentors can direct you in to different resources, but really take advantage of them. You can learn so much about the little devils in the details that'll ruin your design that are hard to quantify by just making a prototype. Cool. You have any questions? I think we're going to end a little early today. Good for you. Yeah. You have any questions? Cool. All right, so we're doing the Kalishnikov lecture on Wednesday, and then Vijay Govindarajan's coming on Monday of next week, the reverse innovation guy. So he told me today, make sure you read the book. Read the sections that I assigned. And I'm going to put a couple other readings up on the website today related to his talk for next week. Good. Thanks, guys.